Thank you for that introduction. All right, so let's talk about machine learning and whether it is hype, whether it's happening, and why businesses fail at it. Now, I know that there are a lot of folks here who are pretty handy with the electronics and hardware side of things, so I have a question for you. Who here knows how a microwave works well enough to build me a brand new one from scratch? Come on, who can do it? Who can build me a microwave? I see a hand. I see one hand. That's very good. That's usually way better than my much larger audiences do. Now, different question for you. Who here has never used a microwave to make food? Okay, also one hand. Different person. Diversity is good. Diversity is good in an audience. Now, for the rest of you, you have just told me that you use microwaves, and yet you have no idea how they work. Why do you trust those things? Why do you let yourself use them if you don't know what that wiring diagram looks like? Well, you're not going to trust them by reading the wiring diagram. You're going to trust them because you're going to think about what you need them to do for you, and then you're going to check that that was actually delivered. And that is also the attitude that you need to take with machine learning if you are applying it to the business. Now, what people don't realize about machine learning, and this is the big place where businesses fail, is that there are actually two machine learnings out there. There is a research side of things, and then there is an applied side of things, or what we at Google are calling decision intelligence. That's our word for applied machine learning and data science, plus. Right? The plus is augmented by the social and managerial sciences. But anyways, there's a research side and an applied side. And these two things are as different as making microwaves from scratch, building general purpose tools for other people to use, that's the research side of things, versus using tools that exist already, maybe with some slight adjustments, to actually cook at scale in the kitchen and innovate in recipes. And here's my analogy for machine learning as well, with all the fancy words on the top and what you can think of them as in plain English and in this analogy. And see, if you are building microwaves from scratch and you're in the business of selling microwaves, you need to actually understand how those things work, and you need to understand that well, because how are you going to make a better microwave than this one if you don't get how this one works? Right? If you're selling microwaves, which is a perfectly legit business to be in. But if, on the other hand, you are operating a kitchen at scale, knowing how that microwave is wired may not be the best thing that you could know about. You need to think about how to get your ingredients, again, at scale, and the logistics of that, and the processing and the checking of them, right, of your data. And you need to think about what your customers need. And you need to think about how you would check that that's delivered and how you would actually go about iterating with all the different microwaves and other kitchen appliances that you have available to you, again, practically and at scale. So making pizza and building microwaves, turns out these are different businesses. And the big failure is that out there companies don't realize that there's a difference between these two. And so they might actually be in the business of selling pizza, but what they do instead is they hire themselves 20 PhD researchers who've been spending their whole lives building little microwave components to run their industrial scale kitchen. I mean, what could possibly go wrong, right? And if that doesn't go wrong, that's not because that was a good decision there and good planning. That's because they got lucky. And they hired themselves a microwave builder who just so happens to be a great chef, who might transcend beyond what they learned in school and look around and get excited about cooking and doing it in practice. And I also find that researchers, they take a funny attitude. They say, oh, when you're talking about decision intelligence, when you're talking about applied machine learning, you're just talking about all that stuff that's a footnote to what we do. Oh, no. If you want to open McDonald's, just because you don't need to wire your own microwaves does not make it easy. There's a whole discipline there. But what the world is doing is training people only for that research side of things. How the algorithms work, that's where all the focus is. Who's training the world how to actually use these things? Because there are warehouses upon warehouses of these microwaves out there already. but who's teaching the world how to cook? Now, I and my colleagues are trying to change that, and so we at Google are training our people in the applied side explicitly, and we're referring to it as its own discipline explicitly because there needs to be awareness and training around this side of things. So that's the big failure part, the not knowing which business you're in. If you want to make microwaves, all the traditional path is exactly what you need, but if you want to use them, you need a different approach. Now, what even is machine learning? Right? I've been using this word over and over, and we often use it, and we don't actually examine our terms. So I'm a statistician by original training. We statisticians, we love to give everything the simplest possible names for stuff. So if we had named machine learning, we would have called it thing labeling with examples. It's just thing labeling. Now, why should you be excited by thing labeling? Well, this is a picture of my pet Huxley, and when you see this, you get the label as if by magic. You just know that it's a cat. And if I show you this one, you're not fooled, you still know that it's a cat. Now, if you want to automate this task the traditional way, you need to, this programmers, you need to communicate in some way with the universe, and you need to come up with the recipe or model that converts the pixels into the answer. And then you handcraft that recipe, then you code it up. What does that recipe need to be in this case? See, you need to tell me what you actually did with each pixel to get the answer cat. And then you need to make sure that it works for both of those situations and a whole bunch of other ones that you're likely to get. What is that recipe? You don't even know, do you? Because your brain just had the benefit of eons of evolution, now it just does this. You don't even know how it does it. So how are you going to code that up explicitly from scratch? Well, wouldn't you prefer instead of giving the instructions explicitly, to say to the computer, here's a bunch of cats, here's a bunch of not cats, now you go figure it out. That is the essence of machine learning. That is what it's all about. Expressing our wishes with examples instead of instructions. So in other words, data, learning from data. And the reason you should be excited about this is not the sci-fi stuff. You should be excited about this because we as humans, we already have two modes of communication that we use to express our wishes to one another. Sometimes we tell people exactly how to do the thing, very micromanagey, and sometimes we say to them, here's a bunch of examples, now go figure it out. And machine learning is that second mode of communication, that other way of programming. It ungags us. It allows us to communicate with computers that second way. So it's incredibly powerful for that. And sometimes we just cannot come up with the instructions because they are too complicated, because they are ineffable. Machine learning allows you to automate the ineffable. It doesn't matter that you don't know how to do the task. You can still get it learned. So that's why it's really powerful. Now, I also want to point out that I am not a hardware type person, and I certainly cannot build you a microwave from scratch. And I know that a conference like this one, the essence in robotics is it's about mind and body, right? You do have to think about the hardware. Whereas what I work on is just the software part, just the mind part, just the learning part. And so that's what this talk is going to be about today. But you can still program your robot body or the traditional, explicit way where you give the instructions and directions and bounds explicitly. Or you could get it all learned from data. So I'm only talking about that mind bit here. And what can you do with it? So machine learning is already here. These are real examples of stuff that you can do, and you should think of this as thing labeling. So a lot of what would be relevant to you is vision stuff, and we have a lot of projects at Google that have to do with vision. So one of our customers, for example, makes satellite image maps, high-quality satellite image maps, and they're not so high quality if they're covered with clouds. So you do a whole bunch of flyovers, and then you remove the cloud information, but you do want to keep the snow. You don't want to do this task pixel by pixel, right? Handpicking which of the white pixels is clouds, which is snow. You would much prefer to get that thing labeled automatically. Another one is catching diabetic retinopathy, so for diagnostic purposes. Is this one healthy, is this one not? Another is someone comes to your door and you have a smart camera and your door can lock if it doesn't recognize the face of the person. Sometimes it works really well, sometimes unfortunately it protects you from Batman. I really enjoyed this Twitter post where the person was locked out of their house on account of Batman being not recognized. Another one is sequences, right? The label doesn't just have to be a single thing, like, do I know this person, don't I? It can be entire sequences, and this may be more on point for what you guys do. So, for example, learning how to play this Atari slider game and coming up with the strategy of tunneling your way up the left side there. It's pretty cool. Then, what's my next move at beating a world champion at the game of Go? That's another thing that you can do with machine learning. Self-driving cars, right? How to actually navigate in an environment. Then, how to control the cooling system of a data center. When we used to do this with traditional data science, and we used to program all those control systems, we'd have data science teams go through and profile things and suggest ways that, again, humans could handcraft some improvements. If you got a 1% to 2% improvement in energy efficiency, that was amazing. And that's a lot of money saved. That's a great carbon footprint reduction. When we gave this over to a fully automated machine learning system, we got a 40% improvement in energy efficiency. Now, data centers, they are expensive things. 40% energy efficiency improvement is huge, and it's a huge reduction in carbon footprints. This is powerful stuff. And then, of course, the last example will be navigating your environment in a sort of robot body like Pepper from SoftBank. Now? Why all this hype around machine learning right now? Actually, a lot of the algorithms have been around for a really long time. They're children of the 60s. But in addition to them, you need data, right? We're learning from examples, so you need examples to learn from, and the world is now collecting data faster than ever before, so now we've got the examples to learn from. But even if you can go and send your agent through the environment and collect a whole bunch of data, you're going to need to store and process that as well. And so in the past, unless you could build your own data center, no way were you going to be able to have a go at this. Today, this is really a story of the cloud, and this is why I'm primarily affiliated with Google Cloud. Today, what the cloud does is it puts all that computing power in your hands so you can take it for a spin, and then if you like what you're doing, you keep going, essentially, with someone else's computers, and if you don't, you haven't built and invested in a whole data center. So now, with the advent of the cloud, now that's why machine learning and AI are becoming so viable. Okay, so that's all the background. Now, how do you avoid the common pitfalls? So the main thing that I started with, I answered my own question of why businesses fail at machine learning. The main thing is know what business you're in. And if you are in the business of solving problems, then try your best to focus on that, hire the right people for solving the business problem, and if you can, get things off the shelf that work and apply them. Whereas if you are in the business of selling general purpose solutions to other people, microwaves, then focus on that. So know what business you're in. That's the biggest piece of advice I have for you. But now, here's 10 other quick tips. First off, do things in the right order if you're in the applied side of things. Don't start with the algorithms, and that's where everyone wants to start because that's what all the training programs are about, right? Don't, for your industrial scale kitchen, make your first move the purchase of the latest range of microwaves or the latest range of pizza ovens. Your first question should be, what am I actually cooking? You don't need the pizza ovens if you're not making pizza. So the first thing you should be asking yourself is, what am I doing here? What business problem am I solving? What dish am I making? What do my customers want? So you start in the sense of inputs, outputs, and models, right, and recipes, You start with the outputs first. That's not where people often start. They want to start with the algorithms, or if they're brought up in data science, they want to start with the data, the inputs. Don't start there. Start with the business. This thing works. It just works. What is it doing? What is it outputting? And then after that, you can move to what the potential ingredients might be that you'd use. That's your data inputs. And then finally, then you go to algorithms. And the first thing you do is you see what's around on the shelf that I can just pick up and use. And if what I need isn't available, then I consider research to build my own. Now, over-focusing on sci-fi, I mean, I feel like I'm going to get a rotten tomato thrown at me at this conference, right? Because we're all about over-focusing on sci-fi. I just want to point out that because of the state of the field since the 50s and 60s, there was a lot of hype, but you couldn't actually do very much without the hardware. So the way you get your grants and the way you stay in business and still be allowed to work on what you want to work on is hype up the sci-fi. And all your grants are sci-fi based. And when you talk about what you're doing, it's all sci-fi based. We don't need to lean on that anymore, friends. It actually works now, and you can do useful stuff with it. And so instead of still having that legacy focus on sci-fi, which makes people unnecessarily nervous of things like paperclip machines and so forth, right? You know that example from the Bostrom book. Instead of that, focus on what you can actually do with it, because it's super useful. It is the labeling of stuff. We don't even need to name it machine learning or artificial intelligence. Think about what it can do and use it and get excited about that. Be driven by greed, right? Next tip, don't reinvent the wheel. So again, I know you want to focus on algorithms first, but a lot of them have already been built and packaged up for you. First, check if what you need exists. And if it does, take it and use it. Maybe adjust it slightly. But don't start from scratch building your own every time. That works when there's not very many wheels, but now that they're there, don't start there. Even though school tells you to start there, don't. Next, it's the basics of learning and teaching and forgetting them. That is where all the problems come in. It's losing track of common sense. You are essentially teaching a student, whether it's a human student or a machine student, to do a task. And so everything that you already know about learning and teaching applies here. So, for example, tip number 5. The input data is essentially a bunch of textbooks. Your student will not learn anything that's not in those textbooks. Unfortunately, the world right now pronounces data, textbooks, examples, with a capital D. Why is data always pronounced with a capital D? Everything is data. It should be pronounced with a lowercase d. But when you pronounce it with a capital D, you also imply this bit of magic around it. Like, if I have textbooks, obviously my student will learn. No, those textbooks have got to be relevant. If your textbooks have a bunch of Japanese English vocabulary pairs, sure, your student will find patterns in them, make a model out of that. It just won't get you a calculus-enabled student, right? So if you want to teach your student calculus, what do you got to do? You got to open those textbooks. You got to make sure that what's in there is actually what you want your student to be learning. And in the robotics realm, sure, you're building your own textbooks and you've got sensors on your machines and you control what part of the environment they see, but there are a lot of choices as well as to how good those sensors need to be, which sensors, which environments. Now, when I talk to engineers at Google, when I train them, I tell them they should pretty much consider tattooing this sentence on themselves if they're going near machine learning. The world represented by your data is the only world that you're going to succeed in. So you need to know what world that is, and you need to think about that really carefully. And your student, human or machine, you have no reason to suspect that your student will work outside of the textbooks, the type of textbooks that they were trained on. Data should not be pronounced with a capital D, and it isn't magic. Now, if you're going to play with reinforcement learning, dealing with sequences of events, there are some joys here in deep RL. So you're dealing with sequences. That's already more difficult than dealing with instantaneous labels like cat, not cat. But also, you're dealing with delayed feedback, and you're dealing with the fact that the choices that your agent makes through its environment affect what data it gets in. So you can get these feedback loops where you become more myopic and silly. And what this really means at the end of the day. On the one hand, sure, there's some implication that you could get a lot of progress in AGI, you could learn any task you wanted, but what it actually means in a practical sense is that you are writing the textbook as the student, as you go along. That is much harder to learn from than a nice set of ready curated textbooks. Oh, and by the way, in the introduction, as I was being introduced to the stage, there was a lot of talk about collecting data. All this data collected about you, you could use this data that's collected. Sure, collected data is useful. You know what's even better? Constructed data that you have curated and made so that it is good to learn from. That's kind of like the difference between giving the student the best possible textbooks, where you have engineered those textbooks to be awesome, you've potentially paid money to humans to sit and do the task for you lots of times to be able to learn it, versus you just passively collected some rubbish from the environment and you put it in a stack and you called that textbooks. That's like the collected data. And then finally, this one, where your student is completely ignorant and is asked to write the textbook while they go along. Which of those is going to be hardest to learn from? So just think reasonably about this. This approach magnifies the amount of data and environmental interactions that you're going to need. And what that means is that your computing just got more expensive. And so for teams and companies, I work for one, that have access to a lot of computing power, we can bite the bullet here and get it done. But if you're planning to do this on your own laptop, that might not work out so well. So tip number 6, simplify where possible. Sure, deep RL is cool and it's hot and it's a nice place to do research, but if you're going to do practical stuff, try your best, if possible, to frame your problem in a simpler way that lends itself to textbooks that are easy to learn from. And also realize that you can put together a whole lot of Lego pieces of things already available. Again, you don't have to reinvent the wheel. So instead of asking your agent to learn to walk through your environment and also recognize the objects that it's seeing, why not consider plugging in some object detection module that's already nicely constructed for you? Then, better data trumps better algorithms. And again, if you are over-focused on algorithms because that's where you grew up, you kind of forget this point. Worry about what's in the textbooks. Worry about your domain selection. Worry about what you're actually collecting from the environment and think sensibly about it. And if possible, improve the logging. Focus there. That's going to pay off quite a lot more than improving the algorithm stuff for the applied side. Of course, if you're in research and you're dealing with algorithms primarily, that's got to be your focus. But for businesses, if you have the choice, focus more of your energy in the data. And then, what keeps you safe with students is not that you understand how your calculus student's brain works, right? You're like, has my student learned calculus properly? I'm going to take a scalpel and dig around in the wet stuff? No, of course not. You don't do that with human students. You won't do that here. Because when the tasks and those recipes get complicated enough, you're not going to be able to open it up and read it, right? By definition, we're forced to go to machine learning and AI when it's too complicated to handcraft it. So because by definition it's now gotten so complicated, it's too complicated for us to read and wrap our heads around. We can't read a million lines of instructions and remember them and make sense of them. Best we can do is oversimplify with analytics, but you're not going to understand it by reading it. The way to check that it's safe is that you test it properly. Just like with calculus, give your student a test. And that test has to have new examples. That whole overfitting thing, that's just memorizing the textbook. How do you protect yourself against the textbook memorized? Make sure that the student couldn't have memorized the example that you test them on. How? Make sure that's a new example. Fairly straightforward. So it's really important to use new data for testing. But then also, it's really important to make sure that that is relevant new data. You want to make sure that you are testing your calculus student at, I don't know, the PhD qualifying exam level. Please, for goodness sake, make sure that the exam isn't 2 + 2 =, right? Make sure that the exam is relevant. And who has to think about that? Well, that's actually the business leader who's thinking about, what am I making here? What does it mean for it to work? Which environment must it be qualified for? And then make sure that your tests actually cover that. Then, number 9. This is the real tricky part, and it's an especial pain if you're in deep RL. Design incentives that cannot be gamed. You need to think about, when you're constructing your reward functions, exactly what you want the thing to learn. Exactly. You need to make sure that you can't have a situation where you get a good score on that exam and it's actually not what you wanted the thing to be doing. That means whoever is designing the exam has to be really good at this. So a simple example, right, with navigating a space would be, you give a negative penalty for falling over. You make it really hard to get a positive reward for navigating correctly, but leaving the space, exiting bounds, is 0 and it terminates the trial. Well, that of course is going to get you a suicidal robot, right? It's really easy to get the huge negative penalty. It's really hard to get the small positive reward. If you exit, ta-da! Now, whose fault was that? It was the fault of whoever thought it was a good idea to make that wish. This is the game of wishing responsibly, yeah? It's like the proliferation of magic lamps as machine learning stuff. You can think of it as that. We're making magic lamps. Instead of making those instructions with the 1,000, 100,000, 100 million lines of code, we are instead making the instruction of, go do your best on those textbooks over there towards this purpose. There we go, that's all you say. Now you've got to put as much effort and care into that instruction as you would have into those 100,000 lines of code. You've got to watch out for that. And typically the person who's responsible for that is the project leader. And they might wish in a stupid way because it kind of sounded good to them. Worry about this stuff. And actually, frankly, you guys should make friends with economists, because economists study this incentive function stuff, and they have excellent feel for this, and they will read and laugh at all these robotics failures where you have made dumb reward functions. They can see it coming kilometers away. And they're trained for that, maybe work with them. But really worry about, if we are making these magic lamps, does your team have the ability to wish responsibly? So that the letter means delivering the letter of the wish also delivers the spirit. Not like, oh, that kind of sounded like a good idea, and then it turns out to be a terrible one. You have to be very careful here. And then finally, to actually run McDonald's at scale, turns out you need a lot of different skills. And you need a lot of different perspectives. Applied machine learning in practice, and this isn't even thinking about the body side, the hardware side, this is just the mind side and the software side. You're going to need, besides the obvious AI engineer trained people, you're going to need statisticians for the testing, you're going to need analysts to figure out which ingredients go in, you're going to need trained leaders to wish responsibly, you're going to need social scientists. There's a lot that social scientists can do, particularly in thinking through stuff like incentive functions, communicating between the leader and the data science team. You're going to need ethicists. We can do it. Should we do it? You're going to need reliability engineers, because your environment might change all of a sudden. How are you going to fix and monitor and maintain it? There are a lot of folks that you need, so you need a diversity of skills and perspectives. And if what you're doing is imagining one ideal, perfect AI professor, and you just want 20 copies of them and that's your team, you're going to fail miserably. Much better to expect a team with different skills and roles that cover the entire set of stuff that it takes to run this kitchen at scale. And be nice to everyone. Right? There's still an attitude around, if you've got the PhD in computer science, robotics, AI, statistics, you're king, otherwise you're just an appendage. That doesn't work. That's really bad for teams, so we're going to need to start changing that attitude as well. And the rest, besides those 10 tips, is much easier than what most people think, because you don't have to start from scratch. A lot of this is already available. You just pick it up and use it. So I hope you have fun with this. So your machine learning adventure awaits. Thank you.